Steven, do you hear me by any chance? I mean, you should hear me, hopefully. Hey, how you doing? Doing well. It's a bonus point?
Yeah, it's the area of velocity.
Thank you, thank you. So we are streaming on YouTube, which is...
Are you going to be sending the YouTube links out now?
I actually put it on the Blackboard Live right now, but I'm gonna send an email with that link right away.
So it's going to be on the emails?
Yeah, it will be on Blackboard essentially, but I will also, like, the announcement will be emailed to you as well. If that makes sense. Hopefully this will have a better quality. The good thing about it is it will upload with the highest quality that is coming on that webcam, and later on the quality of the YouTube video will improve, unlike the Blackboard one. So that's the good thing about YouTube. And I can use a like 4K camera and get a 4K quality like after 2 or 3 days on YouTube. So I will see how it goes. But the link I'm sending is only going to be the link for today's live stream. Okay.
So it's going to be a different link every time.
I mean, I assume that all of the videos will be yeah, will be on the channel. So as long as you click on this link, it will take you to this video, and then you click on the channel, you will have access to other videos. Actually, you will have access to my fluid mechanics and aerodynamics course as well.
I'll have to take fluid mechanics next semester. Can I use that?
You have to take fluid mechanics next semester?
Yeah.
Why though?
I don't know. That's what my advisor.
Who's your advisor?
Her name's Samantha.
Oh,
You are a should say you don't have to take aerodynamics. I would say take heat transfers. As someone who knows more than Samantha about aerospace.
I don't know. I'm still like, I'm ahead on some stuff, but like behind on a lot of stuff. So it's been a confusing track.
You are a sophomore student, right?
I'm a junior.
You are a junior, so you are in the same boat as this. So I would say take. Are you guys taking heat transfer at all? Is this okay? Who did you have? Chen Li, right? Okay.
I'm not taking it.
Okay. It is a. I think it is a course you kind of have to take.
It's a prerequisite for the second aerodynamics course.
Is it?
Yeah.
Okay.
I think I might be taking it.
Second, what is second aerodynamic course?
The one with compressible fluid and all that fun stuff.
the compressor fluid flow 544.
Yeah, 544.
Okay. Yeah. It is a prereq for that one. Okay, so let me start recording on Blackboard. It is. I'm recording on Blackboard. I'm also streaming on YouTube, both of them. The idea is to move to YouTube live stream because I would assume it has better quality. It is going to be easier for you guys to have access to that YouTube live stream. So we already have 2 people present there. It's just one of those people is me. So there's 1 more people, but I don't know who's coming in on the live stream. So you can ask your questions through chat, live stream chat. I'll try to answer any questions you may have. We have 1 question in Blackboard. How would you like us to ask questions? Yeah, that's through the chat. Yeah. Okay. And okay, is there any questions? Class about anything? I think the last thing we covered in the previous lecture was the effects of viscosity, right? That's we essentially started talking about effects of viscosity and viscous fluid flow, right? And about the body layers a little bit, right? We talked about body layers, right? Okay, but we didn't come up with the equation. Let's just to do a small recap. The idea was for an inviscid flow, since we are not including the effects of friction and since we are not including the effects of friction and viscosity, what we are going to get at the layer that is closer to the wall is going to be the same velocity as the far extreme velocity, right? That was the idea. But when you include the effects of viscosity, what you're going to get is going to be a boundary layer. And we also talked about the no-slip condition, which means that on the surface, on the wall, your velocity is going to be 0. Okay. So we're going to get this type of layer around the airfoil in which velocity goes from 0 to 99% of V infinity. That's the definition of this boundary layer thickness, right? That's how we define the boundary layer thickness. And we also mentioned that if we do not include these effects of friction, we won't be able to calculate the friction drag, and we won't be able to have a good understanding of pressure drag as well. We are familiar with pressure drag and friction drag, right? So let's call them, or the pressure drag is also called the form drag or drag by pressure. So if we do not include the effects of friction, we are not going to be able to calculate the friction drag, and we will have a very inaccurate understanding of the pressure drag, which is yeah. But this friction drag for us is going to depend on the thickness of this boundary layer, delta, which is going to be important for us. Okay. So later today, we are going to find ways to calculate this delta essentially. And they're related to the friction coefficient, the wall shear stress, and eventually to the total friction drag on the airfoil. But before doing so, we want to talk about another effect of viscosity. Let me ask you a question. Did you go over these in your aerodynamics? The boundary layer, the calculations, the formulas, and everything. Yes. Okay, so that's good. So we are only going to spend a little amount of time on this. So let's talk about another effect of viscosity or another effect of friction. Another effect. Okay. This effect is very related to Reynolds number. We usually define Reynolds number as the ratio of, not ratio, that's not usually, this is the definition of Reynolds number. The ratio of inertial forces versus viscous forces, right? So when you have low Reynolds number, what you're gonna get is a viscous forces dominant flow, and higher Reynolds number, your inertial forces are going to be dominant. So this dominance of viscous forces is going to cause an orderly flow. Right? The streamlines are all going to be ordered. It's going to be a very orderly flow. I think that's the best way to describe it. And that ordered flow is called the laminar flow. Again, in which the streamlines are very ordered, right? They move on top of each other. It's very nice and orderly. Okay. So our online student is only one, is telling me that he has never done the bio. Have you passed aerodynamics? I guess we have to. Oh, he's also in that. Okay. You'll see these later. You are not gonna need this. I mean, you will learn these in aerodynamics. That's the best thing I can say. How could you take this course then if you haven't taken? It should be a prereq. You definitely have to change that, but that's all right. Pardon me? Can you say that again? I think I have to. I didn't catch it, but that's all right. Let's continue. There were no prereqs. Okay, that's all right. Okay, let's continue. It doesn't really matter. We are gonna go over them anyways, right? So orderly flows, because of the dominance of viscosity, because of the dominance of friction, we're going to get an ordered flow, which is called the laminar. Right? At some point, when Reynolds number increases, and the reason your Reynolds number increases is because on a flat plate, your Reynolds number is going to be the function of the distance from the leading edge here. So as you increase the distance, your Reynolds number is going to increase, right? The rest of them are just free stream parameters, right? X, the distance from the leading edge, right? X. My X's are very crooked, usually. X. Okay? And as you increase as the Reynolds number increases, as you move on the flat plate, on the airfoil, whatever you want to call it, from the leading edge to the trailing edge, inertial forces are going to become more dominant. So what are we going to see when inertial forces become more dominant? Before that's the result. The dominance of inertial forces is the result of the higher Reynolds number, right? That's the idea. That's where we started. So turbulent flow, right? So when inertial forces, there is a cutoff value for Reynolds number, but when inertial forces become more dominant, we're gonna see turbulent flow. And you'll see more about turbulent flow in general if you take a graduate course. Right? It's a very complex type of flow, but we are gonna see a lot of vortices in turbulent flow. So the flow is not ordered. Not ordered. This is what you're gonna see when the inertial forces become. And the idea was, again, Reynolds number here for a plate is a function of your distance from the plate. That's why we define a local Reynolds number. Okay. And we also have an average Reynolds number, or the plate Reynolds number, which is gonna be RE of L. That is going to be rho V infinity L U infinity. Hopefully, we have all heard about the Reynolds number, right? This is not your first time hearing about this. Yes. Okay. So this means this transition, the flow is transitioning. Right? This is another classification: laminar versus turbulence. The flow is transitioning. This is essentially is going to mean that the shear stress is going to change, the amount of shear stress, the way the flow behaves is going to change. So this local Reynolds number is going to be important in our analysis of body layers, which means that it's going to be important in our analysis of friction drag, right? So we have to pay attention to this transition. That's the idea, okay? Any questions so far? Okay. So in general, something that you have to keep in mind is that the gradient, the idea was the velocity has a gradient inside the body layer. It changes, right? You see this as slope, this is going to be your velocity gradient. The velocity gradient is du or dv or y at the wall, where y is equals to 0. For a laminar flow, is going to be smaller than the velocity gradient at the wall for turbulent flow. That's the general rule. That's not a general rule. This is a general observation. This is something that we can see in the experiments, in the experimental analysis. So what does it mean? What does it mean for us, who we don't really care about the fluid analysis or heat transfer analysis part of it? We care about the final conclusions, which is the forces, right? The drag forces, the lift, whatever, right? What is this going to mean for us, fluid mechanics people? You don't know? Take a guess. How can we calculate the shear stress at the wall? Does anyone remember that formula? It was a function of your viscosity, the gradient of velocity at the wall. Exactly. And this W indicates wall, or Y equals to 0. Okay, so when you have a lower velocity gradient for laminar flow, this means lower shear stress, and this shear stress is going to be present in our calculation of the friction coefficient, which is your shear stress divided by the Q infinity, dynamic pressures. Dynamic pressure. So this means that the friction coefficient is definitely going to change from laminar to turbulent. But again, since this Reynolds number, the local Reynolds number, is very important, not only the shear stress is going to be different between the two regimes of the flow, but also it is going to be different at every point, because the local Reynolds number is changing, right? The difference is you're going to see a jump when it transitions from laminar to turbulent. Let's say this is your laminar boundary layer. Then you're going to see a jump in your boundary layer thickness, and everything is going to change. So these are the streamlines inside a laminar. Then you're going to get a very unordered flow. Okay. So shear stress is also local. That's the idea. The same as Reynolds number. It's going to change as we move from laminar to turbulence, which also means that your friction coefficient is also local. What does it mean? Your friction coefficient is going to change over your airfoil. This essentially means that we have to find an average value or total value for the friction coefficient to be able to find the friction force and eventually the friction, which is the friction drag. Is there any question so far? No. Are we all following this? Yes. Well, you tell me you have seen this in your aerodynamics for the people who have passed the aerodynamics, but I don't get it from your faces. Okay, you don't remember that. That's all right. As long as you know what you're talking about. Okay, that's good. That's good. As long as it comes back, right? Okay, so let's actually go see some formulas. We are not going to drive the formulas because that is 2 or 3 lectures by itself. If you end up taking an advanced heat transfer course or a viscous and turbulent flow course, you will definitely see the derivations of these formulas. But I'm just gonna write them down. As I said, this is local, so we need to have some information about whatever that is happening locally at every point inside the boundary layer. The first thing you want to find is the boundary layer thickness, right? Boundary layer thickness for a laminar flow is going to be equal to 5.2 multiplied by x over the square root of Reynolds number, your local Reynolds number. And this is only true for laminar flow. Boundary layer thickness. Okay. And then we already know the general formula for the friction coefficient. Using the boundary layer thickness, you can eventually find through some other equations that we are gonna skip over. You would be able to find the shear stress at the wall, which is going to be, or let's do the friction coefficient first. Friction coefficient at the wall, CFNX, which is 0.664 over your local Reynolds number. And just plug this value in this equation here, you will get your shear stress, right? So your shear stress is going to be Q infinity multiplied by 0.664 over the square root of your local Reynolds number. Okay. And we want to find the total drag force, the friction drag force. How can we relate the shear stress to the total drag force? That's the question we want to answer, right? Let's see if we have any ideas. We want to relate the friction drag to shear stress. Today's a sleepy day, isn't it?
Relate shear stress to Reynolds number and then
Okay. Rel-
like this up.
Relate shear stress to Reynolds number. But we have already done that, right? Just using these two equations, we have already related the shear stress to Reynolds number, right? We want to find that let me put it this way. I want to find the forces due to this shear. This is the friction, right? Force due to that shear. How can I find that? How can you find a force from a stress?
You integrate over the area.
You integrate over the area. That's it, right? Or if it's a uniform distribution of that stress, you just multiply it by the area, right? In our case, it is not a uniform distribution because we have local values and each point is going to be different. So if the whole plate is laminar from 0 to the chord length, we just have to take the integral with respect to the derivative of area. But since we are dealing with a two-dimensional case, we are going to assume we have a unit depth. Your d of area is dx multiplied by 1, right? So it's just one-dimensional. No.
Zero to C.
0 to chord length, right? From the leading edge to the trailing edge. Okay. Or I mean, you can put let's put L, but your book is using L for whatever reason. Okay, so if you just plug in the values, the only x dependence we have here is in the definition of local Reynolds number, right? And we should be able to take this integral. It will give us this value for the total friction drag, 1.328 Q infinity L divided by the square root of rho infinity V infinity L over mu, or the square root of your total Reynolds number. Then we want to define a total friction coefficient to get the final friction drag coefficient. This is going to be capital C. This is the small c. Okay, but you don't see the difference on board. But let's call it CF and L, or CF and C, right? How can we find that total friction coefficient? Using the drag force. Let's go. You just have to go back to the definition of the force coefficient. Which was your friction drag or friction force, whatever you want to call it, divided by Q infinity S, right? And S in this case is L multiplied by 1. Just plug that in. So Q infinity L, plug this value in. Q infinity will cancel out, L will cancel out, and your total friction coefficient for the whole plate or airfoil, whatever that is going to be 1.3.28 divided by the square root of, this is the Reynolds number for the whole plate, RE of L. Is there any questions?
Just to be clear, so the CFX is local and CFL is total.
Yeah. Total average, whatever you want to call it. But this is a value that will give you the friction coefficient of the plate. Okay. And this is you just have to keep in mind that we are doing this analysis assuming that we are really dealing with a very thin airfoil, right? That's usually the assumption we make in our analysis, right? Or a flat plate. Okay, so let's move on to the assumption we were making here in this analysis was that the flow remains laminar, right? Okay, but the idea was whenever inertial forces become more dominant, the flow transitions to turbulence, right? And in reality, what happens is when the inertial forces start dominating the viscous forces, you will see a transitional regime, right, in which you will get some laminar, some turbulent flow, some laminar flow, some turbulent. And after that transitional regime, you're going to get fully turbulent flow. But in our analysis, to make everything simpler, we're just going to assume that that transition happens at one point, right? So we're going to have full laminar, then full turbulence, right? And the idea is where that point is, right? We are gonna call that point the critical length. So critical length is the distance from the leading edge at which your flow is going to transition from laminar to turbulence. Okay. And we're going to use X critical for this. Okay, so how can we find this critical length? That's the gold question, right? But that's a very important question. How can we find this critical length? If the critical length is smaller than the chord length or the length of the plate, we will see transition. So we won't be able to use those formulas to have an estimation of the friction drag, right? Because the transition happens and all those formulas are only true for laminar flow, right? So how can we find this length? Think about it. Okay, so what you're saying is that we can have a single Reynolds number identifying the transition from laminar to turbulence, right? That's what you're saying, and that is true. That goes back to the philosophy behind the dimensionless parameters, right? You can find one dimensionless parameter that is going to identify different types of flow for the same geometry, right? A scaled down and scaled up geometry. Does it make sense? Okay, so what is that cutoff Reynolds number for a flat plate? Does anyone remember? Or from aerodynamics? No? Okay, that's all right. The critical Reynolds number, and this is something that you should try to memorize, is 5 multiplied by 10 to the power 5. And that is true for the transition from laminar flow to turbulent on a flat plate. For the flow inside the duct, the whole thing is different. Reynolds number estimation is going to be different, and that value is going to be different as well. So, and in our course, we don't really care about the flow inside the duct. In this course, we only care about the flow over a plate or over a geometry. Okay, so what you do is you take this Reynolds number, you calculate a critical length using the definition of Reynolds number, rho v infinity multiplied by this x over mu for your specific condition, for your specific velocity, density, whatever. It will give you a value of the critical length, and then you compare it with the length of your plate. If that is smaller, then if that critical length is smaller, this essentially means that this transition happens somewhere here. So we have to do a turbulent analysis as well. What I'm going to do is going to give you the turbulent formulas here. So boundary layer thickness for the turbulent formula, it's going to be essentially the same type of formula. The difference is going to be this number, which is 0.37, and this power, which is 0.2. Yeah, for turbulent flow. Then using this, we would be able to find the CFX, which is also the same type of formula, only the number is going to be 0.592 to the power 0.2. Okay. And this is only the definition of friction coefficient, so this doesn't change for any type of flow regime, right? This is also the same thing here. And then we eventually have the friction coefficient, the total friction coefficient, CF and L, C of F and L is going to be 0.07. I don't memorize these numbers myself, so to the power 0.2. Okay, Reynolds number of the whole plate, and okay, so we have these values, but we are making one major assumption in these formulas. We are assuming that the flow starts as a turbulent flow. Okay, so we are not including the transition yet, not yet. Okay, we are assuming the flow is tripped to turbulence. That's the word they use, or we use, right? Let's say you have a very small thing here. Let's call it a vortex generator, right? And when flow hits this thing on a flat plate, it will become turbulence immediately, and you will get a turbulent boundary layer. So these formulas are only correct in case you have a turbulent, a fully turbulent flow from the start, from the leading edge. Okay. So what should we do if the transition happens? So we start with laminar and we go with transition to turbulent.
Can we just switch the X reference to be the transition point? All these formulas where it's with local.
So what Igor is, I think what you're saying is that to essentially take this as x equals to 0 for the turbulence part, right? But you're essentially omitting a lot of physics, right? If you do that, you are assuming the turbulence boundary layer starts from here, right? That's what the equations analyze. That's what the equation assume, right? So no, that is not a correct way to go about it. But that was an interesting idea. I think I have done the same mistake when I was taking the course, the aerodynamics course, and I lost some point on my exam because of this. But yeah, so any idea? The solution to this is actually pretty simple, right? It's just a mathematical manipulation, right? Or it's just a number game, if you will. I don't know what to call it, but it is a very simple solution. It is not a very like physical aerodynamics related solution. Just something that you can, I'm pretty sure you can come up yourself. I just have to think hard about it. How can we deal with this type of problem where the transition happens somewhere. So the flow doesn't start as turbulent or laminar. Okay, these equations only apply to the cases where the flow starts as turbulent or laminar. Okay, let me ask you this. Let's take a look at this flat plate. And I'm going to explain maybe my question a little more clearly. The equations we have are only applied to a flat plate, right? They only apply to a flat plate for a laminar case when the flow is fully laminar or the flow is fully turbulent. Okay. But in most cases, the laminar may be true, but the turbulent case in most cases is not true, right? They start with laminar, with a very small laminar region, but they transition to turbulent. I mean, in the real world application, the turbulence is usually more dominant, like takes up 98% of the length, and you just neglect the laminar part, right? But the laminar part is going to be there nonetheless. But here, what we want to do is to see what should we do if we have a laminar bilayer that takes up like 40% of the length, for example, just as a number, and then we transition to turbulence. So what Nilov is saying, I assume, and correct me if I'm wrong, is use the equations for the laminar part, use the laminar equations from 0 to the critical point, which is true, right, as you said. But what he is adding for the rest of it is, I think, the same as what Igor said, is to use the turbulent flow analysis for the rest of the problem, which is going to assume this is your turbulent bilayer, right? It's not the real case, right? So what should we do? Double integral of what? It is. Maybe I give you the wrong direction, but I said it's just mathematical game. I meant just a game of addition and subtraction. There is no additional integration involved here.
So we add the boundary layer thickness at the end of the laminar flow to the turbulent flow. So there starts like at a. You know what I mean?
I don't know. I mean, all of you have said the same thing, right? That's essentially that assumes the turbulent bilayer starts from the critical point, which doesn't happen. Turbulent bilayer starts already with a thickness. That's true if we can assume the turbulent flow is dominant, but we are looking at a hypothetical case when the turbulent bilayer is not the most dominant case, right? That's a good question. I can't think of an example off the top of my head, but I assume for a very small like plates in general, it will be the case. Yeah, maybe. Just whatever that has a very small chord then. Okay, we are getting somewhere. Okay, so just forget about the laminar part, right? We can do the calculation, right? And that's fine. We have the laminar conditions. We can find the average friction coefficient, whatever, right? Up until this point, and we should be fine, right? Let's go to the turbulent. Let's say your turbulent body layer is like this, which is the case that happens, right? If it starts from the beginning. We are essentially want to remove this part of the analysis, right? This is the extra part of analysis in that equation for us. We know the critical point. What we can do, we can assume that we have two flat plates, one with this x of critical length, one with the total length, right? Calculate the total force, and you have to do this with the forces, right? That's very important, right? You have to do this with the forces, right? We can calculate the friction drag caused by this turbulent flow, right? From x to 0 critical. It's 0 to x critical. And then we're going to do the same calculation for 0 to L, right? It's if you subtract the two, like subtract these total drag calculations by this one, that is the extra part, you're essentially going to calculate the drag, the friction drag in this part. Does it make sense? So your total drag force, I'm going to write it up here, for a case of transition is going to be drag force of df of laminar, right? Plus the drag force of, I'm just going to call it turbulent and smaller than x critical. This calculation using this x of critical as L in that equation, minus, or it should be actually the other way around, because this will give you the larger value. Your x larger than x critical minus df of t and x smaller for the laminar region. So we do the turbulent analysis, assuming that it starts from 0, the body layer. We just take out the laminar parts from the turbulent analysis. Does that make sense? Is this clear? Yes? No. We are going to solve an example after this. But let me actually try to make it a little more clear. So this part is laminar, like we already know that, right? And we can do the calculation and everything, and from 0 to x of critical, that part is taken care of, right? That part is clear, right? Yes? Okay. And we already know that the equations we have is going to assume that the turbulent body layer starts from 0, which is a wrong assumption, right? So what we do is we use those equations to do two calculations. One calculation for one plate that goes from 0 to critical length, right? Using that turbulent assumption. Okay, and then one calculation for the real plate from 0 to L. You don't, I mean, okay. So this equation is the thing that's throwing you off. When you have the friction coefficient to find the final drag force, you can just use the definition of drag force using this friction coefficient, which is going to be df is cf multiplied by q infinity s, right? We define the friction coefficient or any force coefficient as that force divided by q infinity s, right? So if you have If you have the friction coefficient, you want to calculate the drag force, you just multiply this by these two. Does that make sense? Okay, that's good. Okay. So let's solve. This is the topic that we wanted to cover. We want to go over. This is the review of aerodynamics is done. The only part that remains is the flow separation, which is a very small part, an important part, but very small part nonetheless. And we can talk about the flow separations a little bit. These body layers eventually let's actually talk about the flow separation before jumping into the example. So let's look at a pressure distribution, a real case of pressure distribution, with including the body layer assumption. Where are we? Okay, let me ask you then. How do you think the pressure is distributed, or pressure coefficient is distributed over an airfoil? Where does it start from? Where does it go from there? And so on and so forth. Or do we remember how did we define the pressure coefficient? What was the definition? Pressure coefficient. Does anyone remember? Pardon me? Force coefficients in general always have a relationship with Q infinity. They are always divided by Q infinity. But pressure is force per unit area, so we just drop this area term here. Okay. But what are we going to have on top? This is a pressure coefficient. If it was like friction coefficient, you would have friction drag on top. If it was lift coefficient, you would have lift on top on the numerator. We have the pressure coefficient. What would we have on top on the numerator? Pressure, right? We are not assuming pressure force here because we have already taken that area out, right? So pressure, and based on the definition, we had P minus P infinity, right? That was the definition. Okay. So we have CP. We want to find the distribution of CP versus your length X on this airfoil. What happens is you're going to get with a very high value. Start from the leading edge. You're going to start with a very high value, very close to 1. And then it will go down until it gets to 0, the pressure coefficient. And then, so we have negative values here. Let's say -1. We have +1. Okay. It will reach a minimum negative pressure, but not the negative pressure, negative pressure coefficient. Sorry, no, we don't. But what does it mean for pressure and negative pressure? What does pressure coefficient mean for pressure? It doesn't mean a negative pressure. No, look at the equation. What does a negative pressure coefficient mean? Yeah, so P is going to be smaller than P infinity. That's the only thing that's happening. So at this point, we are going to get the minimum pressure. Okay? Minimum pressure. But notice an interesting phenomenon here, that we have negative slope. The slope of the line is negative, which means your pressure gradient is smaller than 0, right? The slope identified the pressure gradient. So what does it mean? It means that as you move on the lift, on this wing, your pressure is going to be smaller and smaller and smaller, right? But here, you're gonna set a positive. You're gonna see a positive slope, and this is based on observation. This positive pressure gradient is called adverse pressure gradient. So, which means that as you get closer to the trailing edge, your pressure is gonna be higher, right? Let's say we are already at that adverse pressure gradient area here at this point. Pressure here, let's call it 0.1, is going to be larger than the pressure here. What is this going to mean for the flow? Think of a current, electric current. When you have electric current goes from high potential to low potential, but yeah, you can say the same thing for the flow. Flow goes from higher pressure to lower pressure. That's the idea, right? Yeah. No, you have to make a comparison between the pressure distribution on the bottom, right? And that will give you the lift generating area. Does it make sense? Okay. I mean, they may coincide, but this is only an identification, a presentation of pressure distribution on top of the airflow. And this is actually on a flat plate. Yes.
So if the pressure at the very end of the tailing edge is higher than the pressure more towards the leading edge, that what causes vortices on top of the wings?
No, the vortices are in general. I know what you're talking about, but in general, the vortices are caused by the transition to turbulence, right? You're going to see a lot of vortices there, but what we are going to see is that the flow. Let's say it starts from here. Flow is going to move back, not just the vortices. So it's essentially a very consistent flow that is going to be coming back on the wing, right? So it is not just unordered vortices, right? That is going to like fade away, right? This is a very consistent flow. Is going to move back in the opposite direction, right? Because it is being pushed back. Does that make sense? Okay. Yeah.
Where the lower pressure is on the underside of the wing and the air wrap around it. Does that interact with this at all? If you're at the far end of the airflow?
You're going to get the same phenomena on the bottom, on the lower surface as well. So if you have flow separation on top and the bottom, we're going to see these vortices are going to be separate from the wing, and they're going to be essentially the same flow pattern as the separated flow, gets separated from the lower part of the wing. Does it make sense? But I mean, you're gonna see. You will never see more about this unless you take a viscous and turbulent flow course, which is highly recommended if you can take a course. But that's a very interesting course if you are interested in fluid mechanics and aerodynamics in general. Okay, so let's go back to discussion here. Let's say this is the straight line, and here your dp over dx is 0. So at some point, this negative point becomes 0, then becomes positive. This is the point where your flow starts separating from the surface and the flow separation phenomena happens, right? If we do not include the effects of friction, we will never in our analysis, we will never see the flow separation. So, and what's going to happen is that the flow, the distribution of pressure, the pressure distribution on the wing that we are going to calculate is going to be a very inaccurate distribution. I'm pretty sure you have seen the difference in the predictions that you're going to get, the pressure distribution. You're going to get very higher pressure without the friction, or very lower pressure, if you will. Okay. Okay. And you're going to get very lower pressure, which is essentially going to mean a very higher jump back, right? Because it has to jump back, and very higher adverse pressure gradient, but no flow separation. So very unphysical phenomena. Does that make sense? Okay, so if there is no question, let's solve this problem. We have 20 minutes, right? Yeah, we have 20 minutes. I'm gonna give you 5 minutes to solve this problem. And if you are brave enough to come to the board, you will get a bonus point. This is an offer I cannot extend to online students, unfortunately. I'm sorry about it. We'll think of another way to give you bonus points. Yeah, face-to-face students are very happy about this. No. You just the only thing you need to have is bravery. That's it. You can just come here and just look at me. I wouldn't mind. Okay. I mean, at least try, but you'll get the bonus point which reminds me, I haven't given the bonus points. I haven't updated your bonus point on Blackboard. Please, yeah, please remind me if I didn't update it in a week. Okay, if you check that. I think so. Yeah, 0.5. Oh, you see that? So yeah, I have already uploaded. There's someone else who is losing their bonus point, and I'm not sure who that is. So I'm sorry. So this is let's solve this problem. The premise of the problem is telling us that in the incompressible fluid flow, we have already concluded that the aerodynamic forces are proportional to the v squared, v to the power 2 velocity squared, right? Which is not the case when you include the effects of friction. Okay, so we want to actually find that proportionality, right? We are assuming that the aerodynamic forces are proportional to the v to power n, some value n, and we want to find that. We want to find that n value, okay? And I see you want to come to the board, right? Just think about, I'm going to give you 5 minutes to think about it. Try to come up with a solution, and then you can come. We'll solve the problem together, okay? Yeah, that's all right. I mean, you don't have to get the problem right. So we have a flat plate at the lowest speed in compressible flow. The length of each side is 4 meters. So flat plate L equals to 4 meters. And we are going to assume the transition happens at Reynolds number 5 to the power 5. And you have to keep in mind that this is an agreed upon cutoff value. This is not a real cut, because there is no real transition point between laminar and turbulence, right? So this is just an agreed upon value. And the pre-existing properties are those. The pre-existing properties are those at the standard sea level. And we want to calculate the friction drag on the flat plate when the free stream velocity is 20 meters. A, V infinity is 20 meters per second. B, V infinity is 40 seconds per meter. And then eventually, the assumption here is that the friction drag is proportional to the V infinity to power n, we wanna use these 2 points that we are gonna calculate, because we wanna calculate the drag force, the friction drag force, right? We are gonna have 2 points that is going to help us find this n value. Does it make sense?
So what we're looking for to see is
The n, yeah.
Is that an alpha in between?
Proportional. That's df is proportional to. It is. It looks like the Greek letter alpha, but you have seen this proportionality symbol, right? This is the proportionality. I'm pretty sure you have proportionality. How do you write proportional? Proportionality symbol. Is this a correct spelling for proportionality? Who cares? We are not good with the spelling, as we are engineers. I always wanted to buy this T-shirt that says I'm an engineer but with the wrong spelling, like multiple times. That's, yeah. This is especially true for me, because this is not also my native language, not my native alphabet. So but what was the question? Yeah, that's the. Okay, I should work on my handwriting, guys. Sorry. For what?
We never really learned cursive growing up. You read a lot of cursive.
I do. It is very unintentional. So I've learned cursive. Okay. That's a good question. You have to find that out, right? I'm gonna give you we have the sea level properties. So you essentially have to use the density and the viscosity of air at the sea level. And I'm gonna give you those values, but in an exam, you have to find it out from the tables that I'm gonna provide in an exam, okay? So let's see, your mu is 1.789 10 to the negative 5. Mu, viscosity. And your density is 1.23. 1.789 multiplied by 10 to the negative 5. What is the unit for mu? Pardon me? No, it is definitely not unitless. It is a dimension parameter. 1.23. 1.23. That's so. These numbers are. You should be familiar with the range of them at least. Like the air's density at the sea level is around 1. The same as for water density at the sea level is 1,000. Around that value. Okay, so the first thing you want to do is to determine whether we are going to have a transition from laminar to turbulence in any of these two cases. That's the first thing you want to do. Okay. How should we do that? We already have the Reynolds number. Calculate the critical length, right? From the Reynolds number. We already have the transition Reynolds number, right? That's given to us. Okay. So just to speed up the process, I'm going to give you the equations for these parts, and then I'm going to ask Vit to come to the board and I really appreciate your enthusiasm. That's something. In my fluid mechanics class, it's dead. They don't participate for whatever reason. I think they are scared of me, man. Pardon me?
I try my best.
I appreciate that. All of you. I mean, all of you actually participate a lot, and I appreciate that. So we already know this formula exists. For infinity, V infinity x critical to give you the critical length divided by mu infinity. We have these values: 1.798 10 to the negative 5 newtons second per meters squared, and this one is 1.23 kilograms per cubic meters. This is changing between 20 and 40. You have to find the critical length. So what will be this critical length for case velocity of 20, or case A? Yep. Exactly. So for case A, we are going to get critical length of 0.3636 meters. So is this smaller than the 4 meters? Yes. So we will definitely see a transition. Okay. What about the other case, case B? Exactly, because the velocity is 2 times bigger. Thank you. So x critical, what time is it? Is 0.18. So transition happens in both cases. That can be a very good case study for us to see the importance of including the laminar part of the boundary layer. Okay, so let's do the rest of the analysis. The first thing you want to do is to find the friction coefficient and drag force for 0 to 0.336 using the laminar formulas for case A to get the friction drag force of the laminar region. Then you do the same thing for case B to get the drag force of the laminar region again. Okay, and I will give you the bonus points, but hopefully next week you come to the board again. Okay. See, you can get a bonus point with just being enthusiastic. That's sure. What was that?
So you said we would find out if it was laminar or turbulent. And are we going to get that from our DF values?
No. So it is actually based on this Reynolds number, right? This is the agreed upon Reynolds number at which the transition happens, right? So we are assuming if this Reynolds number happens on any part of the plate, the transition is happening at that specific location. Does that make sense? So use this transition. So this is telling us, based on this transition Reynolds number, we are going to get transition at 0.366. Okay? So we already know the transition happens based on this agreed upon Reynolds number. Okay? And then you use the equation to find the drag force for laminar and turbulent flow.
Just comparing the drag force equation, that's the 1.328 L over
Drag, yeah, that should be it, right? Let me just Q. What is Q infinity? That's a good question. That's something you should know as well, right? V infinity squared. That goes back to the definition of dynamic pressure, right? When we were talking about the pitot tubes, we said that you bring down the air velocity from zero, from like whatever that is, v infinity, to zero isentropically, right? And which means that it is going to lose all of its kinetic energy, which is 1/2 rho v squared. So Q infinity is always, yes, go ahead.
So is Q infinity the same thing as Q wall?
Q, yeah. Q, we didn't have Q wall, did we? That's tau of wall. That's the shear stress at the wall. Q is equals to 1, Q infinity in general is 1/2 rho v squared. No, that's, I'm answering someone's question. Sure. Okay. Yeah, let's work on this. We have 4 minutes, but we're gonna get to solve this problem in the next lecture. Since we have 4 minutes, let's work on it a bit. Find the values. We're gonna come back to this problem in the next lecture. I will also post your homework. I think it is dated for Tuesday. I will also post the homework that will cover chapters 1 through 4, but mostly it is going to focus on chapter 4. Probably like 5 or 6 questions. How many questions did I say last on Tuesday? Like 5 or 6 questions, and only 1 question out of these 4 chapters on the exam. On Tuesday, I think that's the date that is listed on syllabus. Yes.
The RECR, that stays the same, right? No matter what.
Yes. That's always this value, 5 times 10 to the power 5. Okay. Did you guys watch the live stream, YouTube live stream? Not you. The online people. Okay. Yeah, YouTube will also notify you. Can you actually try that now? Can you go back to YouTube and try, see if I receive any notification? Okay, you say you just posted a comment, right? Yeah, but I don't see anything. So you are seeing your chats, right? Okay. It was working yesterday though, kind of in my aerodynamics course. So what I'm probably gonna do is continue doing both of them together. Then whenever we figure out YouTube live stream completely without any glitch and any problems, we're gonna move away from Blackboard. Sure. Yeah. No, don't worry. I'll make sure you get the best thing we can provide. Yes, that's correct. Sure. Have a good day. I feel like I'm talking on the phone. So I guess that's it for today's class. We are already at the 11:20 mark. So let's stop here. Let me